Tonight, we're going to talk about something that's been hiding in our own cosmic backyard, something so massive, so distant, and so deeply unsettling that even the astronomers who first proposed its existence speak about it in cautious, measured tones. There is something out there beyond Neptune, something that pulls on the orbits of distant icy worlds, something that bends gravity in ways our solar system shouldn't allow, something that, according to the math, has to exist. And yet, after more than a decade of searching with the most powerful telescopes ever built, no one has found it. By the end of tonight, you're going to understand what scientists have discovered out there in the darkness, why they're terrified that confirming its existence could rewrite everything we thought we knew about our solar system, and why some researchers are quietly suggesting that what we're hunting for might not be a planet at all. Before we go deeper, if you love the idea of exploring the unknown corners of our cosmos, take a moment to like the video or subscribe. It's a small action, but it helps this channel reach more curious minds like yours. Now let's begin. The story doesn't start with a telescope. It starts with a piece of ice. Far beyond Neptune, in a region so cold and so empty that sunlight from our own sun appears as nothing more than a particularly bright star, there are millions of frozen objects drifting in slow, silent orbits. This region is called the Kuiper Belt. It begins around 30 astronomical units from the Sun, just past Neptune's orbit, and extends outward to about 50 astronomical units. Pluto lives there. So do thousands of other dwarf planets and icy bodies that have never had warmth, never had air, never had anything resembling the conditions we'd call hospitable. They've been drifting in the dark since the solar system formed 4.6 billion years ago. For most of human history, we didn't know any of this existed. The Kuiper Belt was theoretical until astronomers finally began detecting its objects in the 1990s. And as our telescopes improved, as we catalogued more and more of these frozen worlds, something strange started to emerge. Something the astronomers couldn't ignore. Something that didn't fit. In 2014, two researchers named Chad Trujillo and Scott Shepard published a paper that quietly upended planetary science. They had been studying a small group of extremely distant trans-Neptunian objects, frozen worlds so far from the Sun that they take thousands of years to complete a single orbit. And they noticed something that shouldn't have been there. The orbits of these distant objects were clustered. They were aligned. They pointed in the same direction, tilted in the same way, like a row of arrows, all aimed at the same invisible target. This shouldn't happen. In a normal solar system, distant objects should have randomly oriented orbits. There's no reason for them to align. The Sun's gravity affects all of them roughly equally at those distances. The known planets, including Neptune, are too close to the Sun to influence objects that far out. By every law of physics we understand, those distant icy worlds should be drifting in chaotic, uncorrelated paths. Instead, they were marching in formation. Something was herding them. 2 years later, in 2016, two astronomers at the California Institute of Technology took this observation and turned it into a hypothesis. Their names were Mike Brown and Konstantin Batygin. Mike Brown, ironically, is the astronomer most famous for getting Pluto demoted from planet status. He had spent years arguing that Pluto wasn't truly a planet, and now he was suggesting that a real planet, a true ninth planet, was hiding in the darkness beyond Neptune. The universe has a sense of humor. Brown and Batygin ran the numbers. They modeled the orbits of those clustered objects. They tested every conventional explanation. Random chance. They calculated the probability of the alignment happening naturally at roughly 0.007%. Effectively zero. Some unknown gravitational effect from the known planets. The math didn't work. Some statistical bias in how the objects were discovered. Possible, but vanishingly unlikely given the sample. Every explanation failed except one. There had to be another planet out there, a massive one, and it had to be at a very specific distance, in a very specific orbit, with very specific properties to produce the gravitational shepherding they were observing. Their conclusion was breathtaking. They predicted a planet 5 to 10 times the mass of Earth, a world larger than our own, but smaller than Neptune, orbiting the Sun at an average distance of around 400 to 800 astronomical units. That's 20 to 30 times farther from the Sun than Neptune is. To give you a sense of that scale, light from the Sun takes about 4 hours to reach Neptune. Light from the Sun would take more than 4 days to reach Planet 9. A single year on this hypothetical world would last between 10,000 and 20,000 Earth years. Think about that. While humans were domesticating wheat in the Fertile Crescent, this planet had just begun a single orbit. While the Egyptians were building the pyramids, it had barely moved. While Rome rose and fell, while every empire in history rose and fell, this planet was completing a tiny fraction of one trip around the Sun. It moves so slowly through the darkness that from our perspective it would appear almost stationary, just a faint smudge of light against the deep black background of space, drifting imperceptibly across the years, if it exists. And that "if" is the entire problem. Because despite the elegance of the math, despite the gravitational signatures that keep showing up in the data, despite the alignment of those distant icy worlds, no one has actually seen this planet. Not the Hubble Space Telescope, not the Subaru telescope on Mauna Kea, not the dedicated wide-field surveys that have been scanning the outer solar system for the past decade. The most powerful instruments humanity has ever built have searched, and searched, and searched. And they have found nothing. This is what makes Planet 9 such a profoundly uncomfortable scientific puzzle. The evidence for its existence is mathematical, it's gravitational, it's statistical, but it's not visual. We can detect its fingerprint on the orbits of distant worlds. We can model its mass, its location, its trajectory. We can predict roughly where in the sky it should appear. And then we point our telescopes there and we find empty space. There are several explanations for why this might be. The most straightforward is also the most frustrating. Planet 9, if it exists, is incredibly faint. At 400 to 800 astronomical units, the sunlight reaching it is roughly 1 million times weaker than the sunlight reaching Earth. The light reflecting off its surface and traveling back toward us is weaker still. By the time those photons cross the vast emptiness and arrive at our detectors, they're so dim they're nearly indistinguishable from the natural background noise of the cosmos. Finding Planet 9 is like trying to spot a candle on the surface of the moon from your backyard. The light is technically there, but picking it out from everything else is extraordinarily difficult. There's another problem, though, and it's the one that makes some astronomers genuinely nervous. We don't actually know exactly where to look. Planet 9's orbit is highly elliptical. At its closest approach to the Sun, it might be around 200 astronomical units away. At its farthest, it could be 1,200 astronomical units or more. Most of the time, it spends in the far, slow, distant part of its orbit, drifting through regions of space we haven't fully mapped. The hypothetical orbital path traces a long oval across roughly 30% of the sky. Within that area, we have to find a single faint point of light, moving so slowly that it barely changes position from one observation to the next. It gets worse. The orientation of the orbit means Planet 9 could currently be passing through one of the densest regions of stars in our galaxy, the plane of the Milky Way. Looking toward Planet 9 from Earth, our line of sight might be aimed directly at thousands upon thousands of background stars. The planet's faint light would be drowned out by the brilliant stellar foreground. It could be sitting right in front of us, in plain sight by cosmic standards, and we still wouldn't see it because the background is too bright. But here's where the story takes a strange turn. Because as the searches continued and the planet remained stubbornly invisible, some researchers started asking a different question. What if it's not a planet at all? In 2019, two physicists named Jacob Scholz and James Unwin published a paper that proposed something so bizarre it sounded like science fiction. They suggested that the gravitational anomaly we're calling Planet 9 might actually be something else entirely. A primordial black hole. A small, ancient black hole left over from the earliest moments of the Big Bang. Not a stellar mass black hole formed from the collapse of a dying star. Those are at least 3 solar masses, far too large to fit the gravitational signature we're detecting. Something smaller, something far stranger. A black hole roughly the mass of 5 to 10 Earths, but compressed into an object the size of a grapefruit. A grapefruit. A black hole the size of a piece of fruit, orbiting our sun, herding distant icy worlds with its gravity, completely invisible because it emits no light. reflects no light, and is far too small to detect with any conventional telescope. If this is what Planet 9 actually is, we would never find it by looking for reflected sunlight. It would simply not be there to see. We would only ever detect its presence through its gravitational effects on other objects. Exactly the kind of evidence we've been gathering for the past decade. This idea sounds absurd at first, but the math works just as well for a primordial black hole as it does for a conventional planet. And primordial black holes have been a hypothesis in physics for decades. They could theoretically form in the chaotic first instance, after the Big Bang, when the density of the universe was so extreme that small regions might have collapsed directly into black holes. If even a small fraction of dark matter consists of these primordial objects, they could be scattered throughout the universe. And if our solar system happens to have captured one during its formation, it might be sitting out there right now in a long, slow orbit, perfectly invisible, perfectly impossible to confirm, and perfectly capable of producing every gravitational signature we've observed. Whether Planet 9 is a world or a black hole, what we're really hunting is something that has been hiding from us since before humans existed. Something that has shaped the architecture of our solar system in ways we're only beginning to understand. And the deeper we look, the stranger the implications become. To understand why scientists are so cautious about confirming Planet 9, you need to understand what its existence would actually mean. Not just for our maps of the solar system, not just for textbooks, for our entire theory of how planets form, where they belong, and what's possible in the architecture of a star system. Because if Planet 9 is real, it doesn't fit. It doesn't belong where it is. And the explanations for how it got there are, every single one of them, deeply uncomfortable. Let's start with what we know about planet formation. When our solar system was young, about 4.6 billion years ago, it was nothing more than a vast disk of gas and dust swirling around the newly ignited sun. This disk, called the protoplanetary disk, extended out to perhaps 50 astronomical units, maybe a little farther. Within this disk, small particles of dust began to clump together. They collided, they stuck, they grew. Over millions of years, these clumps became pebbles, then boulders, then planetesimals, then protoplanets. Gravity did the rest. The largest objects swept up the smaller ones, clearing their orbits, becoming the planets we know today. The inner solar system, closer to the Sun, formed rocky worlds: Mercury, Venus, Earth, Mars. The heat from the young Sun prevented volatile compounds like water and methane from condensing, so only metals and silicates could form solid bodies. Farther out, beyond the so-called frost line, ices could solidify. There was more material available. The planets that formed there grew enormous. Jupiter, Saturn, Uranus, Neptune, gas giants and ice giants, each massively larger than anything in the inner solar system. And then, beyond Neptune, the disk thinned out. There simply wasn't enough material at those distances, and the orbital periods were so long that particles rarely encountered each other to clump together. So no large planet should have formed out there. The Kuiper belt is full of small icy bodies, but nothing approaching the size of a true planet. That's the problem. Planet 9, if it exists at 400 to 800 astronomical units, is sitting in a region where it could not have formed. There wasn't enough raw material at that distance. The orbital dynamics wouldn't have allowed it. Our understanding of planet formation says it shouldn't be there. And yet, according to the gravitational evidence, it is. This forces scientists into a corner. They have to explain how a planet 5 to 10 times the mass of Earth ended up in a place where planets aren't supposed to be. And every explanation they've come up with is, in its own way, profoundly strange. The first possibility is that Planet 9 formed closer to the Sun and was then ejected outward. In the chaotic early days of the solar system, the gas giants were not in their current orbits. Jupiter, Saturn, Uranus, and Neptune all migrated significantly. They moved inward and outward, exchanging gravitational energy with smaller bodies and with each other. During this period of instability, smaller protoplanets could have been flung into wildly different orbits. Some were ejected from the solar system entirely, sent off into interstellar space as rogue planets. Others might have been thrown into the outer reaches, but not quite hard enough to escape the sun's gravity. They settled into long, slow elliptical orbits, captured in the cold darkness far from where they were born. If Planet 9 formed near Jupiter or Saturn, it could have been ejected outward by a close gravitational encounter with one of the gas giants. The energy of that encounter would have flung it onto its current orbit. It would be a refugee from the inner solar system, a planet that was supposed to live close to the sun, but ended up exiled to the outer darkness. The second possibility is even stranger. Planet 9 might be a captured exoplanet, a world that formed around another star entirely. In star clusters, where young stars are born close together, gravitational interactions can rip planets away from their parent stars and toss them between systems. Our Sun was born in such a cluster around 4.6 billion years ago. During that time, before the cluster dispersed, the gravitational chaos could have allowed our young Sun to capture a planet from another star system. That planet would have settled into a wide, distant orbit, perfectly compatible with where Planet 9 is theorized to be. If this is true, Planet 9 is not really one of us. It's a stranger, an immigrant from another solar system. A world born around an alien sun that ended up in our cosmic neighborhood through nothing more than gravitational accident. The third possibility is the most extreme. Planet 9 could have formed in place through some process we don't fully understand. Perhaps the protoplanetary disk extended much farther than we think. Perhaps unusual conditions in the outer solar system allowed a planet to coalesce out there despite the thin material. This would mean our models of planet formation are incomplete. It would mean there are mechanisms operating in protoplanetary disks that we haven't accounted for. And it would mean other star systems might also have similar distant planets that we haven't detected. Each of these explanations carries weight. Each is plausible. But each also opens new questions that current science can't fully answer. And that's why the search for Planet 9 isn't just a search for a single world. It's a search for a piece of evidence that will tell us how our solar system actually came to be. The answer is hiding out there in the dark. Now let's talk about what would happen if we did find it, what it might actually be like, because the descriptions astronomers have constructed are genuinely strange. Planet 9, based on the gravitational signature, is probably what astronomers call a sub-Neptune or super-Earth, larger than our planet but smaller than Neptune. Its mass would be somewhere between 5 and 10 Earth masses. Its diameter would be perhaps 2 to 4 times that of Earth. This puts it in a category of planet that doesn't exist anywhere else in our solar system. We have rocky worlds and we have gas giants, but there's a gap between them. No intermediate worlds, no super-Earths or sub-Neptunes. Yet ironically, when astronomers survey other star systems, they find that super-Earths and sub-Neptunes are among the most common types of planets in the galaxy. Almost every solar system has one, except, apparently, ours, unless we count Planet 9. If Planet 9 exists, it would mean our solar system isn't actually unusual. It would mean we have the most common type of planet. We just couldn't see it because it's so far away. Our cosmic neighborhood would suddenly look much more typical of what we find around other stars. What would the surface of such a world look like? Almost certainly frozen. At 400 to 800 astronomical units from the Sun, the temperature would be brutally cold, perhaps minus 220 degrees Celsius or lower. Any atmosphere it possesses would consist mostly of hydrogen, helium, and trace amounts of heavier gases that hadn't yet frozen out. The clouds would be made of methane and ammonia ice crystals. The pressure at the surface, if there is anything we could call a surface, would be enormous. Beneath those frozen clouds, layers of high-pressure ice might cover a rocky core. It would be a world of perpetual twilight, where the sun appears as nothing more than a brilliant star, never warming the surface, never illuminating more than a fraction of the landscape. A world where day and night are nearly indistinguishable, where seasons last for thousands of years, where the sky is filled with stars even at noon. If there are moons, and a planet of that size would almost certainly have captured some, they would orbit in this same frozen darkness. Tiny ice worlds drifting around their parent planet, themselves trapped in orbits that take centuries to complete. The entire system would be silent, motionless, locked in a deep cosmic stillness that has persisted for billions of years. And here's something that should genuinely unsettle you. There may not be just one. The gravitational analysis that suggests Planet 9 exists doesn't actually require a single object. It requires a particular gravitational signature. That signature could come from one massive planet, or it could come from multiple smaller bodies arranged in just the right configuration. Some researchers have proposed that the anomaly might be explained by a ring of unseen mass in the outer solar system, not a single planet at all. Others have suggested it might be a primordial black hole, as we discussed. Still others wonder if there could be multiple distant planets, all influencing the orbits of the Kuiper belt, objects together. The data can't yet distinguish between these possibilities. We know something is out there. We just don't know what. The implications go even deeper. If we have one undetected planet at 400 to 800 astronomical units, why couldn't there be others farther out? The Oort cloud, the spherical halo of icy bodies surrounding our solar system, extends to perhaps 100,000 astronomical units. That's a vast, almost unimaginable region of space. Most of it has never been mapped. Most of it has never been observed. There could be planets, brown dwarfs, captured rogue worlds, primordial black holes. Anything could be hiding in that immense darkness. Our solar system might be far larger and more complex than we ever imagined. The familiar map of 8 planets, an asteroid belt, and a Kuiper belt could be a profound oversimplification. The real solar system might extend much farther, contain many more bodies, and have an architecture more elaborate than anything our textbooks describe. This is what scientists are afraid of, not that Planet 9 exists. The existence of one more planet wouldn't be a crisis. What's unsettling is what it would mean. It would mean our maps are incomplete. It would mean our theories of how planets form and migrate are missing important pieces. It would mean the solar system we thought we understood is actually a mystery. We've explored it with spacecraft, mapped its planets, photographed its moons, sent probes to its outer edges. And yet there could be a world larger than Earth hiding in plain sight, gravitationally tugging on objects we've catalogued for decades, and we still haven't found it. That should make you wonder what else we've missed. Because if a planet 5 to 10 times the mass of Earth can stay hidden, what else is out there? What other secrets is our own solar system keeping from us? And more importantly, how much of what we think we know about the cosmos is actually wrong? The hunt for Planet 9 is one of the most ambitious search efforts in modern astronomy. And to appreciate just how difficult it is, you have to understand the scale of what we're looking at. The outer solar system is not a small place. It's not even a large place by ordinary standards. It is staggeringly, almost incomprehensibly vast. The volume of space we're searching is so enormous that the human mind struggles to grasp it. And somewhere in all that emptiness, drifting through the cold and the dark, is a single faint object we're trying to find. Let me give you some perspective. Imagine the sun shrunk down to the size of a basketball, about 30 centimeters across. At that scale, Earth would be a small pea orbiting about 30 meters away. Mars would be a slightly smaller pea at about 45 meters. Jupiter would be a softball at 150 meters out. Saturn would be a smaller ball at 290 meters. Uranus and Neptune would be marbles at 580 and 900 meters, respectively. And Planet 9, if it exists at 600 astronomical units, would be a small ball about the size of a tennis ball, sitting almost 5 kilometers away from your basketball sun. 5 kilometers. To find it, you would have to scan that entire spherical volume of space, searching for a single tennis ball somewhere in a region the size of a small city, in complete darkness, with only the faintest reflected sunlight to guide you. And that's just the inner part of the search region. If Planet 9 is at the far end of its orbit, it could be at 1,200 astronomical units. That would put your tennis ball almost 10 kilometers away. The volume of space we have to search grows with the cube of the distance, which means doubling the search radius means searching 8 times as much space. The numbers escalate quickly into absurdity. Now consider that the tennis ball isn't sitting still. It's moving. Slowly, but moving. Over the course of a single year, Planet 9 would shift its position by only a tiny amount, perhaps just a few arc minutes against the background stars. That's roughly the apparent width of a small crater on the moon. To detect motion that subtle, you have to take images of the same patch of sky months or years apart and compare them with extreme precision. Most automated surveys don't have the time, the resolution, or the patience to do this for every possible target across 30% of the sky. Then there's the brightness problem. Planet 9, if it exists, would be incredibly faint. Astronomers estimate it would shine at somewhere between magnitude 22 and 25 in visible light. To give you a sense of what that means, the human eye can see down to about magnitude 6 under perfect dark sky conditions. Each step in magnitude represents about a 2.5 times difference in brightness. So magnitude 22 is about 250,000 times fainter than the dimmest star you can see with your naked eye. Magnitude 25 is about 4 million times fainter. To detect light that faint, you need long exposures with very large telescopes. You need to gather photons one at a time, accumulating signal over minutes or hours, hoping that what you're seeing isn't just random noise in your detector. And here's the cruel irony. Even with all of that, even with the most sensitive instruments in the world taking long, careful exposures of the right region of sky, you might still miss it, because Planet Nine's exact location is uncertain. The gravitational analysis gives us a probable orbit, but the planet could be anywhere along that orbit right now. It could be near its closest approach, where it would be brighter and easier to detect. Or it could be near its farthest distance, where it would be at its faintest and slowest moving. The probabilities favor the latter, simply because objects spend more time at the far end of an elliptical orbit. Planet 9, if it exists, is almost certainly in the most difficult part of its orbit to observe right now. That's not bad luck. That's just orbital dynamics. It moves slowly when it's far away and quickly when it's close, so we're statistically more likely to catch it in the slow, distant phase. Despite all of these obstacles, the search continues. And it's been going on for years now, with increasing sophistication and increasing urgency. The Subaru telescope, an 8.2-meter instrument located on Mauna Kea in Hawaii, has been one of the workhorses of the Planet 9 hunt. Its hyper-suprime cam is a wide-field camera that can image enormous patches of sky in a single exposure. Mike Brown himself has used Subaru for years, methodically scanning the sky regions where Planet 9 is most likely to be. So has Scott Shepard, one of the original researchers who identified the orbital clustering. They have collectively swept across substantial portions of the predicted search area, and so far they have found nothing definitive. What they have found, however, is interesting in its own right. Each survey has discovered new trans-Neptunian objects, new distant icy worlds that were previously unknown. The catalogue of known extreme objects has grown, and as it has grown, the statistical case for Planet 9 has both strengthened and weakened in unpredictable ways. Some new discoveries fit the predicted pattern perfectly, providing additional evidence that something is herding these orbits. Other discoveries fit less well. They don't show the expected clustering. They might suggest that the original observed alignment was a statistical fluke, an artifact of how the first objects were discovered rather than a real physical signature. This is the messy reality of frontier science. The evidence pulls in different directions. Different researchers interpret the data differently. Some are confident Planet 9 is real, and we just haven't found it yet. Others have grown increasingly skeptical, arguing that better and more complete surveys are starting to weaken the original case. The debate plays out in academic papers, in conference talks, in long discussions among researchers who have devoted years of their careers to this question. Nobody knows the answer yet. Nobody can be certain. A new tool is about to change everything. In Chile, high in the Andes Mountains, sits the Vera C. Rubin Observatory. After years of construction and testing, it began its survey operations in 2025. This is not just another telescope. It is a fundamentally different kind of instrument designed for exactly the kind of problem Planet 9 represents. The Rubin Observatory has a primary mirror 8.4 meters in diameter, but what makes it special is its camera. The LSSD camera, which stands for Legacy Survey of Space and Time, is the largest digital camera ever built for astronomy. It has 3.2 gigapixels and can image an area of sky roughly 40 times the area of the full moon in a single exposure. What this means in practical terms is that Rubin can scan enormous portions of the visible sky every single night. Its planned mission is to image the entire southern sky every 3 to 4 nights, repeatedly, for 10 years. This will create an unprecedented time-lapse view of the cosmos. Anything that moves, anything that changes, anything that flickers or shifts position will be detected. The data archive will eventually contain billions of objects, with multiple observations of each, allowing astronomers to track motions, identify variables, and find faint moving targets across the entire sky. For Planet 9, this is the ultimate hunting machine. Where previous searches had to choose small patches of sky and observe them carefully, Rubin observes everything, all the time. Where previous searches were limited by how much sky a single human could analyze, Rubin will use sophisticated automated software to flag every potentially interesting moving object. Where previous searches might have missed Planet 9 because they happened to look at the wrong patch of sky at the wrong time, Rubin will eventually cover every patch many times over. If Planet 9 exists within the visible range of the telescope, and if our predictions about its brightness are roughly correct, Rubin will find it, possibly within the first few years of its survey. This is one of the most exciting prospects in modern astronomy. Within the next decade, perhaps within just a few years, we will likely have a definitive answer to whether Planet 9 exists. Either Rubin will detect it, photographing it as a slow-moving point of light against the background stars, and we will have confirmed the existence of a ninth major planet in our solar system. Or Rubin will complete its survey without finding anything, and we will have to reckon with the fact that the gravitational anomalies we've observed have a different explanation. Either outcome would be revolutionary. Either outcome would force us to rewrite parts of our understanding of the solar system. But here's something to consider. Even if Rubin finds Planet 9, that won't be the end of the story. In some ways, it will only be the beginning. Because once we have a real position, a confirmed orbit, and reliable observations, we'll want to study this world in detail. We'll want to learn what it's made of. We'll want to understand its composition, its atmosphere, its temperature. We'll want to know whether it has moons, whether it has rings, what its magnetic field looks like. All of these questions require sustained observation with multiple instruments. Some require space-based telescopes capable of detecting infrared emissions. Others might require dedicated spacecraft missions to actually visit the planet. And visiting Planet 9, if we choose to do so, would be one of the most ambitious projects humanity has ever undertaken. The current record for the most distant spacecraft is Voyager 1, which launched in 1977 and is now about 165 astronomical units from the Sun. It took 48 years to get there. Planet 9, at 400 to 800 astronomical units, is at least 2.5 to 5 times farther. Even with the fastest propulsion technologies we currently have, sending a probe to Planet 9 would take half a century or more. The entire careers of the scientists who design the mission, who build the spacecraft, who launch it, would pass before the probe arrived. The people who finally analyze the data might be the grandchildren of the engineers who started the project. This is the strange truth about Planet 9. It is close to us, at least by interstellar standards. It is within our own solar system. It orbits our own sun. And yet it is so far that reaching it would require generations of dedicated effort. It is part of our cosmic family, and yet utterly alien, frozen, distant, and almost impossibly remote. We share a star with it. We share a gravitational system with it, and we have never seen it. We may never directly see it in any meaningful detail within our lifetimes. Let me take you somewhere now. Not in our imagination, but in our minds, to the place where Planet 9 should be. Because to truly appreciate what we're hunting, you need to understand what that part of space is actually like. The outer solar system isn't just dark. It isn't just cold. It's a region so profoundly different from anything we experience that it functions almost as another universe, governed by different rhythms, different scales, different fundamental conditions. Picture yourself standing on the surface of Planet 9. If we're being honest, you couldn't actually stand on it, because a planet that size would either have a thick gaseous envelope you would sink through or a solid surface so cold and pressurized that you would die in moments. But indulge the thought experiment. Imagine somehow you could stand there, looking up, breathing, alive, witnessing. The first thing you would notice is the silence, not just the absence of sound, though there would be that. There's no atmosphere thick enough to carry sound waves at any meaningful intensity, but more profoundly, the silence of motion, of activity, of the kind of cosmic vitality we take for granted on Earth. There would be no wind to speak of, though faint stirrings of methane and hydrogen might drift across the landscape. There would be no rain, no waves, no rustling vegetation, no animal calls, no human conversation, no machines, no music, nothing. Just the perfect quiet of a world that has never been disturbed by anything alive. The second thing you would notice is the sky. Looking up, you would see a sky filled with stars. The same stars we see from Earth, but more of them. So many more. Because there would be no atmospheric haze to blur them, no light pollution from cities, no scattered sunlight to wash out the faint ones. The Milky Way would arch across the sky like a luminous river of stars, vivid and detailed in a way no earthbound observer has ever truly seen. The constellations would be subtly different too, because from 600 astronomical units away, our perspective on nearby stars would have shifted slightly. The familiar shapes of Orion and Ursa Major would still be recognizable, but the geometry would feel just a little off, like a photograph taken from a slightly different angle. And among all those stars, one of them would be unique, brighter than any other. Sharp, brilliant, a pinprick of intense white light. That would be the sun. Our sun. The star that gave birth to everything we know. From this distance, it would appear about 360,000 times dimmer than it does from Earth. Still bright by stellar standards, perhaps as bright as the full moon from Earth. But it would be a point, a pinpoint, not a disk, not a source of heat, just a particularly luminous star, lost in the vastness, indistinguishable to the naked eye from the other bright stars surrounding it. If you knew exactly where to look, you might detect a few other dim objects near the sun. These would be the inner planets and the gas giants, faint specks reflecting that distant starlight back into the darkness. Earth itself, from Planet 9, would be essentially invisible. The entire civilization of humanity, all our cities, all our history, all our achievements and tragedies, would be reduced to nothing more than a tiny smudge of light, occasionally hidden in the glare of the sun. We would not exist as a planet from that perspective. We would be a hint, a rumor, a glimmer too faint to resolve. The third thing you would notice is the cold, not just cold by Earth standards, cold by physical absolutes. The temperature on Planet 9 would hover somewhere around 50 Kelvin, give or take. That's roughly minus 223 degrees Celsius. To put that in perspective, the coldest temperature ever recorded on Earth was at the Soviet Vostok station in Antarctica in 1983. It registered minus 89 degrees Celsius. Planet 9 would be more than twice as cold. At those temperatures, water doesn't just freeze, it becomes harder than steel. Carbon dioxide freezes into dry ice. Methane, which is a gas on Earth, becomes a liquid and then a solid. Nitrogen, which makes up most of our atmosphere, would liquefy and rain down as snow. The cold on Planet 9 isn't just unfriendly. It is hostile to chemistry itself in ways that make the development of complex molecules, let alone life as we know it, almost inconceivable. But here's something strange. Despite the profound cold, despite the distance from the sun, despite the apparent inhospitability of the outer solar system, scientists have been quietly asking a question that would have seemed absurd a generation ago. Could Planet 9 harbor some form of life? The answer is almost certainly no, in any conventional sense. But the question itself is interesting, because life on Earth has shown us, over the past several decades, that it can thrive in conditions we used to think were impossible. There are bacteria living in volcanic vents at the bottom of the ocean, surrounded by superheated water and toxic chemicals. There are organisms in the dry valleys of Antarctica that survive in soil so cold and arid it seemed sterile. There are microbes found miles deep inside solid rock, sustained by chemical reactions in the absence of sunlight. There are extremophils that live in pools of acid, in saturated salt brines, in the cooling water of nuclear reactors. The boundaries of life keep expanding the more we look. And then there are the moons of the outer planets. Europa, the moon of Jupiter, has a global ocean of liquid water beneath its icy crust. kept warm by tidal forces from its giant parent. Enceladus, a small moon of Saturn, has geysers of water erupting from its south pole, indicating subsurface liquid water and possibly hydrothermal activity. Titan has lakes and rivers of liquid methane and ethane, and beneath its surface there may be a layer of liquid water. Even Pluto, a tiny world far past Neptune, has shown signs of geological activity. These places suggest that the outer solar system, far from being a dead, frozen wasteland, might actually be filled with hidden environments where exotic forms of life could potentially exist. If Planet 9 is a true planet, several times the mass of Earth, it would have significant internal heat. Some of that heat would come from its formation, residual energy, from the gravitational compression that built the planet. Some would come from radioactive decay in its rocky core. Some might come from gravitational interactions with any moons it possesses. Combined, these sources could be enough to maintain liquid water beneath an icy crust, a subsurface ocean. Not on the surface, where the cold is too extreme, but deep down, insulated by miles of ice, kept warm by the planet's own internal energy, there could conceivably be vast hidden seas. And in those hidden seas, in absolute darkness, with chemistry instead of sunlight as the energy source, who knows what might exist? This is speculation. We have no evidence whatsoever that Planet 9 harbors life. We have no evidence Planet 9 even exists. But the possibility, however remote, is part of what makes this story compelling. Because the outer solar system, far from being the dead, empty void we once imagined, is turning out to be one of the most interesting regions in our cosmic neighborhood. And Planet 9, if it's there, would be the largest world in that region, the dominant gravitational presence, the lord of the outer dark. Now let me describe something else about the place where Planet 9 lives. The way time works there is genuinely strange. We measure time on Earth in years, defined by our orbit around the Sun. One Earth year is about 365 days. That's our fundamental unit of planetary time. But Planet Nine's year would be approximately 10,000 to 20,000 Earth years long. A single orbit. One trip around the Sun. Think about what that means. Human civilization, in its entirety, fits within roughly one orbit of Planet 9. The first cities of Mesopotamia, the pyramids of Giza, the rise and fall of Rome, the medieval era, the Renaissance, the Industrial Revolution, the World Wars, the Digital Age, everything we collectively call human history occupies less than a single year on Planet 9. From Planet Nine's perspective, if it had a perspective, all of humanity's existence is roughly equivalent to a single day on Earth. We are a brief flicker, a momentary disturbance. Something that happened on a small planet during one passing season of its long, slow orbit. This kind of temporal scale is difficult for humans to internalize. We are short-lived creatures built for fast cycles. We measure our lives in years, our memories in decades, our histories in centuries. Planet 9 measures its years in millennia. It moves so slowly through the darkness that an entire generation of astronomers can observe it without seeing it shift position by a meaningful amount. Empires can rise and fall while it crosses just a tiny arc of its orbit. The cosmic scale of its existence dwarfs our own in ways that make even the most ancient human structures seem young by comparison. And this is just one planet in our solar system, one of presumably many. Because Planet 9 is just the closest candidate among potentially countless other distant objects. The Oort cloud, that spherical shell of icy bodies surrounding our solar system, extends from perhaps 2,000 astronomical units to 100,000 astronomical units. That's 50 times farther than Planet 9. The orbital periods of objects in the Oort cloud can be measured in millions of years. Some of them complete a single orbit in the time it takes a species to evolve. Some take longer than that. Comets that visit our inner solar system periodically have come from the Oort cloud. Halley's Comet, which we see every 76 years, is a relatively short-period comet. Comet Hale-Bopp, which appeared spectacularly in 1997, has an orbital period of about 2,500 years. Comet C199501, also known as Hale-Bopp's parent population, might have orbits of tens of thousands of years. And there are likely comets out there with orbits of millions of years that haven't visited the inner solar system since before humans existed and won't return until long after we're gone. Within that vast, distant region, there could be many objects we haven't detected. Planet 9 is just the gravitational signature that we happen to notice first. There could be others. There could be a Planet 10, or rogue planets passing through, or primordial black holes, or things we haven't even imagined. The outer solar system, in other words, is a frontier. It is the largest unexplored region in our immediate cosmic neighborhood, and it is hiding secrets that we are only just beginning to uncover. Planet 9 is the most famous of those secrets, but it is probably not the only one. Now we have to confront something that makes this story even stranger. Because while astronomers have been searching for Planet 9, hunting for that single gravitational signature in the outer dark, a different group of researchers has been quietly raising an uncomfortable possibility. What if Planet 9 isn't a planet at all? What if what we're detecting is something far more exotic, far more ancient, and far more disturbing than a frozen world drifting in the cosmic distance? This idea first emerged in 2019 when two physicists named Jacob Scholz and James Unwin published a paper in the journal Physical Review Letters. The title was deceptively dry, but the content was extraordinary. They proposed that the gravitational anomaly we've been calling Planet 9 could be explained by a primordial black hole. Not a stellar black hole, the kind formed when massive stars die. Those are too large, with minimum masses of around 3 solar masses. Anything that big in our solar system would be obvious. It would devour everything around it, emit radiation as material fell in, and dominate the dynamics of the entire outer system. We would have detected it long ago. A primordial black hole is different. These are hypothetical objects that, if they exist, formed in the very first instance after the Big Bang. Not from the collapse of stars, but from the collapse of regions of incredibly dense matter that existed when the universe was less than a second old. In those chaotic primordial conditions, small fluctuations in density could have caused tiny patches of the early universe to collapse directly into black holes, before any matter had even formed atoms, before any structure existed, before time as we measure it had really begun. These primordial black holes could come in any size, from microscopically small to enormously massive. And here's what makes them theoretically attractive for explaining Planet 9. A primordial black hole with a mass of 5 to 10 Earths would be tiny, perhaps the size of a grapefruit or a baseball. It would emit no visible light. It would reflect no sunlight. It would be effectively invisible to every telescope we have. But its gravitational signature would be exactly what we'd expect from a small planet at the right distance. It would tug on the orbits of distant trans-Neptunian objects in exactly the way the actual data suggests something is doing. In other words, every observational test we've used to look for Planet 9 assumes we're looking for a planet. We're looking for reflected sunlight. We're looking for thermal infrared emissions. We're looking for the visual signature of a large, cold world. A primordial black hole would pass every gravitational test while failing every visual one. It would be there, herding the orbits, exerting its influence, and yet completely impossible to see with any conventional astronomical technique. The longer we search and fail to find Planet 9 as a planet, the more the primordial black hole hypothesis gains traction by default. Not because the evidence for it is stronger, but because the alternative keeps failing. If this is what we're dealing with, it's almost more disturbing than finding a planet. A planet is at least familiar. We know what planets are. We have 8 of them. We have detected thousands more around other stars. They fit into our understanding of how solar systems work. A primordial black hole is something else entirely. It would be a relic of the very birth of the universe, captured by our solar system at some point in its long history, drifting in a slow elliptical orbit, completely undetectable except through its gravity. It would be older than the sun, older than any planet, older than any star. It would have been wandering through the cosmos for billions of years before our solar system existed, and it would have been incorporated into our cosmic neighborhood through pure gravitational accident. How would such an object have ended up in our solar system? There are a few possibilities. The most likely is that our young sun, born in a dense star cluster, captured the black hole during the chaotic gravitational interactions of that formative period. Just as we discussed earlier with the captured exoplanet hypothesis, our solar system could have grabbed onto something from the surrounding space. If primordial black holes are even moderately common, if they make up some fraction of what we call dark matter, then some of them would inevitably pass close to forming star systems. Most would zip through without being captured. A few might be slowed down enough by gravitational interactions to settle into long-bound orbits. One of them might be sitting in our outer solar system right now. What would it actually be like out there? A primordial black hole the mass of 5 Earths, but the size of a grapefruit, sitting in the vast darkness, completely invisible, dominating the gravity of its region, but emitting nothing. It would have no event horizon in the dramatic sense we picture from movies. The event horizon of an object that's small would be only a few centimeters across. To approach it would be unimaginably dangerous. The tidal forces near such an object would tear apart any matter that got too close, stretching it into a thin stream of plasma that would spiral into the hole, emitting a faint glow of X-rays in its final moments. But the region where this could happen is so small that the probability of any significant amount of material drifting into it is vanishingly low. Most of the time, the black hole would simply sit there, silent and dark, exerting its gravitational influence on distant orbits without consuming anything. There are ways we might try to detect a primordial black hole if it exists. One approach involves looking for the brief flashes of light produced when small bits of matter, perhaps comets or icy debris, occasionally do fall into it. These flashes would be subtle, hard to distinguish from other transient phenomena, but if you knew where to look and how to search, you might catch one. Another approach involves gravitational wave detection, though the wavelengths produced by such a small object orbiting alone would likely be beyond our current capabilities. A third approach involves searching for any pattern of microlensing, where the black hole's gravity briefly amplifies the light of background stars as it passes in front of them. Microlensing has been used to detect dark objects in other parts of the galaxy, and dedicated surveys could potentially detect a primordial black hole in our solar system if we knew its approximate location. So far, none of these approaches have succeeded. Either Planet 9 is a planet, and we just haven't found it yet, or it's a primordial black hole, and we don't yet have the techniques to detect it, or it doesn't exist at all, and the gravitational anomalies have some other explanation. The data continues to allow all three possibilities. The mystery deepens with every passing year of fruitless searching. But let's pause for a moment and consider something even stranger. What if the anomaly we're seeing isn't a single object at all? What if it's the gravitational influence of many small objects distributed throughout the outer solar system, collectively pulling on those distant trans-Neptunian orbits? Some researchers have proposed exactly this. They've suggested that instead of a single planet or a single black hole, there might be a population of relatively small objects in the outer solar system. A diffuse ring of mass at the right distance, exerting collective gravitational influence on the visible Kuiper belt objects. This idea has some appeal because it doesn't require any single dramatic discovery. It doesn't require a missing planet. It doesn't require an exotic black hole. It just requires that there be more material in the outer solar system than we currently know about. And given that we've already underestimated the number of small bodies in the outer solar system many times over, this isn't actually a wild stretch. Every time we improve our surveys, we find more trans-Neptunian objects. Every time we extend our reach, more frozen worlds appear. Maybe the gravitational signature is just the cumulative effect of all the unmapped material out there, and there's no single dramatic object to find. The trouble with this hypothesis is that it requires a fairly specific distribution of mass to produce the observed clustering effects. Not impossible, but it has to be just right. And testing it directly would require an even more comprehensive survey of the outer solar system than what we're currently doing. We would need to find and catalogue every small body across enormous regions of space, characterize their orbits, and verify that their combined gravity could indeed produce the patterns we see. This is a much harder problem than finding one bright planet, and it would take decades of survey work to definitively prove or disprove. There's another wild possibility that some researchers have considered. What if the alignment of orbits we've observed isn't caused by any gravitational influence at all? What if it's an artifact of how we've been looking? When you survey the sky, you have biases. You can only detect objects that are bright enough to see. You can only find them at certain points in their orbits when they're closer to the sun. You're more likely to discover them in certain regions of the sky than others, depending on where you've been pointing your telescopes. All of these selection effects can create apparent patterns in your data that aren't actually present in reality. Some researchers have argued, quite seriously, that the orbital clustering attributed to Planet 9 might be exactly this kind of statistical illusion. The original sample of extreme trans-Neptunian objects was small. Subsequent discoveries have shown a less clear pattern. Maybe what we thought was a real cosmic signature was just an unlucky coincidence in our first observations. Maybe Planet 9 doesn't exist at all. Maybe there's nothing out there beyond Neptune except the ordinary scattered population of icy worlds we'd expect. If this turns out to be true, it would be its own kind of disappointment. But it would also be its own kind of relief, because it would mean our solar system is more orderly than we feared. It would mean the outer dark doesn't hide unsettling secrets. It would mean we understand what's out there after all, and we don't need to invoke exotic physics or unexpected objects to explain what we see. The truth is that nobody yet knows which of these possibilities is correct. Planet 9, primordial black hole, diffuse ring of mass, or statistical illusion. Each remains live. Each has its advocates and its critics. Each makes different predictions about what we should observe next. And that's why the Vera C. Rubin Observatory is so important. Within its survey, we should finally have enough data to distinguish between these possibilities. Within the next few years, we may know. To really understand what Planet 9 would mean for our understanding of the cosmos, we have to step back and look at the bigger picture. Not just our own solar system, not just the search for one missing planet, but the broader question of how planetary systems actually work throughout the universe. Because for decades, we believed our solar system was a kind of cosmic standard. We thought the architecture of 8 planets, with rocky worlds close to the sun and gas giants farther out, represented something like the default configuration. We thought other star systems would look mostly like ours. And we were wrong about that. Profoundly wrong. The discovery of exoplanets, worlds orbiting other stars, began in 1992 with the detection of planets around a pulsar. 3 years later, in 1995, astronomers found the first planet orbiting a sun-like star, a world called 51 Pegasi b, and from that moment, our understanding of planetary systems started to crumble. Because 51 Pegasi b was not what anyone expected. It was a gas giant roughly half the mass of Jupiter, but it was orbiting its star at a distance closer than Mercury orbits our Sun. It completed a full orbit in just 4 Earth days. This was supposed to be impossible. Gas giants couldn't form that close to a star. The heat would prevent gas from collecting into a planet. Our theories of planet formation, developed by studying our own solar system, said such worlds shouldn't exist. But there it was. And as more exoplanets were discovered, the picture only got stranger. Astronomers found hot Jupiters, gas giants orbiting incredibly close to their stars. They found super-Earths, rocky planets much larger than our own. They found sub-Neptunes, intermediate worlds with properties between Earth and Neptune. They found planets in tight orbits, planets in wide orbits, planets in elliptical orbits, planets in retrograde orbits going the wrong way around their stars. They found systems with multiple stars and planets orbiting in complex configurations. They found systems where planets were tightly packed together, others where they were spread thinly across enormous distances. Most disturbing of all, they found that our own solar system seemed to be unusual. The most common types of exoplanets in the galaxy, super-Earths and sub-Neptunes, are completely absent from our system. We have nothing between the size of Earth and the size of Neptune. This gap between rocky worlds and ice giants is something of an anomaly. Most other star systems studied so far have at least one planet in that intermediate range. We don't. Unless, of course, we have Planet 9. This is one of the reasons astronomers find the Planet 9 hypothesis so compelling, even in the absence of direct observation. If it exists, it would put our solar system more in line with what we see elsewhere. It would mean we have the most common type of planet. We just couldn't see it because of its extreme distance. The architecture of our solar system would suddenly look much more typical of what the galaxy produces. But even with Planet 9, our system would still be strange in other ways. We have a relatively orderly arrangement of planets in roughly circular orbits, all moving in the same direction in roughly the same plane. Many other star systems are far more chaotic. They have planets in highly elliptical orbits, planets crossing each other's paths, planets in violent gravitational interactions that constantly reshape the system over millions of years. Our system, by comparison, looks tranquil, stable, almost designed. That apparent order is what makes the existence of Planet 9 even more puzzling. Because if our solar system is so orderly, why does it have this one giant outlier? Why would a planet, several times the mass of Earth, end up in a wildly elliptical orbit far beyond Neptune, when everything else stays close to the plane and follows nearly circular paths? The answer, of course, is that something dramatic must have happened. Something that ejected one planet outward while leaving everything else intact. Or something that brought one planet inward from elsewhere while everything else continued in its original configuration. The leading hypothesis is that early in our solar system's history, there was an instability among the gas giants. Jupiter, Saturn, Uranus, and Neptune did not form where they are now. They formed closer together, and over the first few 100 million years, they migrated outward as they exchanged gravitational energy with smaller bodies. During this migration, the dynamics could become chaotic. Smaller protoplanets that formed in the same region as the gas giants could be flung outward by gravitational encounters. Some were ejected from the solar system entirely. Some were scattered into the Oort cloud, where they joined the icy bodies on long elliptical orbits. And some might have been thrown onto orbits intermediate between the planets and the Oort cloud, lasting orbits that we now call extreme trans-Neptunian. Planet 9 could be one of these scattered protoplanets. A world that formed in the inner regions of the early solar system, perhaps somewhere near Saturn or Uranus, that got too close to one of the gas giants and was flung outward. Its trajectory wasn't quite fast enough to escape the sun's gravity entirely, so it settled into a wide elliptical orbit, where it has been ever since. From this perspective, Planet 9 isn't an oddity. It's a survivor, the last visible relic of a chaotic era when our solar system was being violently reshaped. Most of its siblings were ejected into interstellar space. One of them, perhaps the largest, was retained in a marginal orbit, and there it has remained for 4.5 billion years, drifting through the cold dark, while life evolved on the inner world it had once known. This kind of history isn't unique to our solar system either. Astronomers studying exoplanets have found evidence that planet ejection is incredibly common. Rogue planets, worlds that aren't orbiting any star, drifting alone through interstellar space, are now estimated to be at least as numerous as planets bound to stars. There might be hundreds of billions of them in our galaxy alone. Some of these rogue planets were probably ejected from their parent systems during chaotic early periods, just like the protoplanets that might have been thrown out of our own system. Some might never have orbited any star at all, having formed directly from the collapse of small clouds of gas and dust in interstellar space. The galaxy is teeming with planets that don't fit our familiar picture of planetary systems. And here's something to consider. If Planet 9 is real and was scattered onto its current orbit during our solar system's chaotic youth, then somewhere in interstellar space right now, drifting through the darkness between stars, there might be other worlds that were once part of our solar system. Planets that were flung out completely, that never settled into any stable orbit, that are still moving outward through the galaxy at thousands of kilometers per second. They could be anywhere by now. Some might have passed close to other stars, perhaps even been captured by them. Some might be drifting through the void, untethered from any system, slowly cooling toward absolute zero. Some might have been studied by astronomers around other stars, if any such astronomers exist, who might wonder where these planets came from. They came from us, from our system. from a violent era 4.5 billion years ago when our cosmic neighborhood was being reshaped by gravity and chance. This is the bigger picture that Planet 9 fits into. Solar systems are not eternal, stable configurations. They are dynamic, evolving, sometimes violent places. Planets can be born, ejected, captured, destroyed. The arrangement we see today is just a snapshot in time. 4 billion years ago, our solar system looked completely different. 4 billion years from now, when the sun begins to die and swell into a red giant, the system will look different again. Mercury, Venus, and possibly Earth will be consumed by the expanding sun. The outer planets will continue their long, slow orbits, perhaps for hundreds of millions of years more, but the system will eventually disperse. The sun will become a white dwarf, slowly cooling over trillions of years, and most of what we know as our solar system will fade into the dark. Planet 9, if it exists, will outlast much of what we currently see. Because of its extreme distance, it would survive the sun's red giant phase. While Earth boils and Mercury is destroyed, Planet 9 would barely be affected. It would continue its slow orbit, undisturbed by the death of its parent star. After the sun shrinks to a white dwarf, Planet 9 would still be there, drifting in its long elliptical orbit, illuminated only by the faint thermal glow of the dying stellar remnant. It would witness the slow cooling of our solar system over time scales we can hardly imagine. Trillions of years. Long after humanity has gone, long after Earth has been consumed, long after the sun has faded to a black cinder in the dark, Planet 9 would still be there, the last great relic of our cosmic neighborhood. Eventually, even Planet 9 would face its own fate. Over the immense time scales of cosmic evolution, gravitational perturbations from passing stars, and the slow effects of galactic tides would gradually destabilize its orbit. After perhaps 100 billion years or more, it would either fall back toward the dead remnant of our sun or be flung outward into interstellar space, joining the population of rogue planets that wander the galaxy. By that time, the universe itself would have changed dramatically. Stars would be much rarer than they are today. The era of star formation would be ending. The galaxy would be sparser, colder, dimmer. Planet Nine's fate would unfold in a universe approaching its long thermal death. This is the truly cosmic scale of what we're talking about. A single planet, if it exists, with a story spanning the entire history of the solar system and possibly beyond. From its formation in the early chaos of our system, through the eons of slow orbit, through the death of its parent star, through the gradual destabilization of its trajectory, all the way to its eventual fate in a darkening universe. Planet 9, in this sense, is more than a planet. It is a witness, a silent observer of cosmic history, a thing that has been and will be, persisting through ages we can barely conceive. And yet right now, in our present moment, we can't even see it. We don't know if it exists. We don't know what it is. We are arguing about whether it's there at all. The most ancient and persistent object in our solar system might be hiding in plain sight, and we are not yet capable of confirming its presence. There's something humbling about that, something that puts our human achievements in perspective. Let's return to the question that opened this exploration. Why are scientists hesitant to confirm Planet 9? What is it about this hunt that makes researchers cautious, careful, sometimes openly uncomfortable? On the surface, it would seem like the discovery of a ninth planet should be the most exciting scientific announcement of the century, the kind of breakthrough that would inspire generations, the kind of finding that would dominate headlines for years. So why the hesitation? The answer is more complex than it first appears. And to understand it, we have to look at the history of similar discoveries, both successful and embarrassing, that have shaped how astronomers approach the announcement of new worlds. The most famous cautionary tale is the story of Vulcan, not the planet from Star Trek, but a real hypothesized planet that astronomers searched for during much of the 19th century. The story begins with French mathematician Urbain Le Verrier, one of the great theoretical astronomers of his era. In 1846, Leverrier had performed one of the greatest predictive feats in the history of science. He had noticed that the orbit of Uranus didn't match the predictions of Newtonian gravity. There were small but persistent deviations. Leverrier calculated that another planet, more distant than Uranus, must be tugging on it gravitationally. He predicted where this planet should be, sent his calculations to the Berlin Observatory, and within a single night of observation, astronomers found Neptune almost exactly where Leverrier said it would be. It was a triumph. Mathematical prediction had led directly to physical discovery. The power of gravitational analysis was vindicated. Leverrier then turned his attention to Mercury. The innermost planet had its own orbital anomalies. Its perihelion, the point of closest approach to the Sun, was slowly shifting in a way that couldn't be fully explained by the gravitational influence of the other known planets. Leverrier, fresh from his success with Neptune, applied the same reasoning. He calculated that there must be another planet, this one inside Mercury's orbit, that was perturbing it. He predicted a small world close to the Sun and named it Vulcan, after the Roman god of fire. For decades, astronomers searched for Vulcan. They reported seeing it during solar eclipses. They claimed to have detected its transit across the face of the Sun. Leverrier himself died in 1877, believing Vulcan existed. The astronomical community accepted its likely existence for years. There were textbook entries, scientific papers, illustrations of the supposed planet. And then, in 1915, Albert Einstein published his theory of general relativity. And general relativity explained the anomaly in Mercury's orbit perfectly, without needing any additional planet. The shifting perihelion of Mercury was a relativistic effect, caused by the warping of spacetime near the Sun. Vulcan didn't exist. It had never existed. The reported observations had been errors, wishful thinking, misidentifications of sunspots, and other phenomena. The entire decades-long search had been pursuing a phantom. This story haunts modern astronomy because the parallels to Planet 9 are uncomfortable. Like Vulcan, Planet 9 is predicted from gravitational anomalies. Like Vulcan, it has resisted direct observation despite intense searching. Like Vulcan, there are alternative explanations for the data that don't require any new planet to exist. Many astronomers, remembering the Vulcan affair, are determined not to repeat that mistake. They want hard evidence. They want a photograph. They want a confirmed orbit calculated from multiple independent observations. They don't want to announce a discovery based on gravitational signatures alone, only to have the planet turn out to be a mathematical illusion. There are other cautionary tales too. In the early 20th century, Percival Lowell, a wealthy American astronomer, became convinced that there was a planet X beyond Neptune. He used gravitational analysis, similar to what Leverrier had used for Neptune, examining apparent anomalies in the orbits of Uranus and Neptune. Lowell calculated where this planet X should be and spent years searching for it. He died in 1916 without finding it. In 1930, a young astronomer named Clyde Tombaugh, working at the observatory Lowell had founded, discovered Pluto. It was hailed as the predicted Planet X, the world Lowell had been seeking. The story was almost too perfect. A wealthy founder leaves behind unsolved predictions, and a young astronomer at his observatory completes the mission. Except it wasn't true. Pluto turned out to be far too small to produce the gravitational anomalies Lowell had been analyzing. It was a coincidence that Pluto was found near Lowell's predicted position. The original anomalies in Uranus's and Neptune's orbits were ultimately explained by improved measurements of Neptune's mass. There was no Planet X in the sense Lowell had imagined. Pluto was a real discovery, but it wasn't the discovery anyone had expected. The story of Planet X became another lesson in how mathematical predictions can mislead astronomers and how confirmation bias can shape what we think we've found. These episodes are part of why the current Planet 9 search is so carefully scrutinized. Astronomers know that gravitational anomalies don't always point to undiscovered planets. They can point to errors in measurement. They can point to misunderstood physics. They can point to statistical illusions in small data sets. The challenge is to do the analysis carefully, to consider every alternative explanation, to be honest about uncertainty, and to wait for direct confirmation before declaring victory. But there's another reason for the caution, and this one is more sociological than scientific. The astronomy community is small, interconnected, and deeply reliant on reputation. A wrong announcement can damage a career. A premature claim of discovery can lead to embarrassment, retraction, lasting reputational harm. Mike Brown, the astronomer who has done so much to advance the Planet 9 hypothesis, is particularly aware of this. He spent years arguing that Pluto wasn't really a planet, going head-to-head with researchers who passionately disagreed. He's been right about controversial questions before, and he's also been the target of intense criticism. He knows that announcing a ninth planet without direct observation would invite enormous skepticism. He's been careful to frame the hypothesis as a strong inference from gravitational evidence, not as a confirmed discovery. He's waiting for the visual proof that would silence all doubts. This caution is healthy in science. It's how the field protects itself from false claims, from publication of mistakes, from the kind of high-profile errors that can damage public trust in scientific findings. But it also means that real discoveries can be delayed, debated, and questioned for years before they're accepted. Some Planet 9 researchers believe they have already accumulated overwhelming evidence that something is out there. Others believe the case is still circumstantial. The debate continues, even as the searches do. There is yet another layer to this cautiousness, though one that goes beyond the typical professional caution of astronomers. Some researchers have suggested, sometimes quietly and sometimes openly, that confirming Planet 9 could have implications they are not entirely sure how to handle, not in any supernatural or pseudoscientific sense, but in the very real sense that it would force significant revisions to our models of solar system formation, planetary dynamics, and possibly the structure of dark matter or the nature of primordial black holes. Imagine for a moment that the Vera Rubin Observatory begins its survey, and within a year it identifies a slow-moving object at the predicted distance for Planet 9. The light curve doesn't quite match what astronomers expected. The reflectivity is wrong. The thermal emission, when measured by infrared telescopes, doesn't fit any known planetary composition. After months of analysis, the conclusion becomes inescapable. What we found isn't a normal planet at all. It's something else, something we don't fully understand. A captured rogue from another star system, a primordial black hole, a type of object we've never observed before in our solar system. The news would not be the simple discovery of a ninth planet. It would be the announcement of something deeper, something stranger, something that requires the rewriting of multiple chapters of textbook science. That kind of discovery is both exciting and disturbing for those who study it. Exciting because it represents a profound advance in knowledge. Disturbing because it means our existing understanding was significantly incomplete. Disturbing because it raises further questions about what else might be out there that we haven't yet detected. Disturbing because it suggests that our solar system, which we thought we understood, has been keeping major secrets from us for as long as humans have looked at the sky. This is the uncertainty that makes some scientists genuinely uncomfortable, not the discovery itself, but the implications that follow from it. Because if we found Planet 9 and it turned out to be exotic, the next question would be obvious. What else have we missed? How confident should we be in our maps of the cosmos? How many other anomalies in the data are we ignoring or misinterpreting? How many discoveries are waiting to be made in regions we haven't fully explored? There's a sense in which finding Planet 9, particularly if it turns out to be something unexpected, would be a wake-up call. A reminder that the universe still has surprises in store. A reminder that even our local cosmic neighborhood is not fully understood. A reminder that the foundations of our knowledge are perhaps less solid than we've assumed. And let's be honest about something else. There's also a deeply personal dimension to this. Researchers who have spent their careers building careful models of the solar system have an emotional investment in those models being correct. Not because they're stubborn, but because their work, their reputations, their lifetimes of effort are tied up in those models. A discovery that overturns major aspects of those models would be challenging in human terms. It would force people to reconsider conclusions they reached years ago, to admit errors, to embrace new frameworks that may not yet exist. That's not easy for anyone, even for scientists who pride themselves on intellectual honesty. The Planet 9 hunt isn't just a technical search. It's also a test of how the astronomy community handles uncertainty, how it manages the prospect of fundamental revision, and how it balances the desire for discovery with the need for caution. All of these forces converge in the present moment. The data is suggestive but not conclusive. The hypothesis is plausible but not proven. The technology to confirm or refute it is finally coming online. The community is watching, debating, predicting, hopping. We stand at a threshold. Within a few years, we will likely know the answer. Let's now turn to something that often gets lost in the technical discussion of Planet Nine, the deeper philosophical implications. Because beyond the question of whether this world exists, beyond the question of what it might be, there is a more profound question lurking underneath. What does the search for Planet Nine tell us about ourselves, about our place in the cosmos, about the limits of human knowledge? For most of human history, the night sky was a mystery. Our ancestors looked up at the stars and wondered. They constructed stories about the gods who lived among them. They built calendars based on the movements of celestial bodies. They navigated by the constellations. But they didn't truly understand what they were seeing. The planets were thought to be wandering stars, special objects whose motions held divine significance. The fixed stars were thought to be lights on a great sphere surrounding the Earth. The Earth itself was assumed to be the center of everything. It took thousands of years of careful observation, patient calculation, and revolutionary thinking to dismantle these assumptions. Copernicus placed the sun at the center, displacing Earth from its privileged position. Galileo turned his telescope to the heavens and saw moons orbiting Jupiter, mountains on the moon, phases of Venus. Kepler discovered that planetary orbits weren't circles, but ellipses. Newton formulated the laws of gravity that explained why. With each step, our understanding of our place in the cosmos shifted. We were not at the center of anything. We were one planet among many, orbiting one star among countless others, in one corner of an unimaginably vast universe. This story of cosmic demotion, sometimes called the Copernican revolution, has continued through history. Every major discovery has further humbled us. We learned that our sun is just one star among hundreds of billions in our galaxy. We learned that our galaxy is just one among hundreds of billions of galaxies. We learned that the universe is expanding, accelerating, perhaps infinite. We learned that we are made of the same atoms as everything else, the same matter that was forged in the cores of dying stars billions of years ago. We are not special. We are not central. We are not unique. We are part of something vastly larger than ourselves, and our existence is, in cosmic terms, fleetingly brief. Planet Nine represents the next chapter in this story, because if it exists, it would mean that even our local cosmic neighborhood, the place we thought we knew, contains hidden worlds. It would mean that the solar system we mapped in textbooks is incomplete. It would mean that for all our scientific achievements, for all our spacecraft and telescopes and theoretical models, we still don't fully understand what's in our own backyard. There is a world possibly 5 to 10 times the mass of Earth, sitting somewhere out there in the dark, and we have not seen it. We have only inferred its presence from the way it pulls on distant icy bodies. It is, in a very real sense, hidden from us. And the fact that something so massive can hide from us, even now, in the 21st century, with all our technology, is humbling. It makes you wonder what else is hidden. Not just in our solar system, but everywhere. What other planets exist around nearby stars that we haven't yet detected? What other phenomena are operating throughout the universe that don't fit our current models? What other gravitational anomalies are we ignoring because we don't yet have the tools or the theoretical framework to interpret them? The history of science is full of examples of things hiding in plain sight, things that turned out to be obvious in retrospect, but invisible before someone found the right way to look. Dark matter, for instance, dark energy, the cosmic microwave background, the structure of atoms, the double helix of DNA. All of these existed long before they were discovered. They were hidden from us not because they were rare or distant, but because we didn't yet know how to find them. Planet Nine, if it exists, is in this same category. It has been there the whole time. It has been pulling on those distant orbits for billions of years. Astronomers have been looking at the sky for centuries, and the planet was there, somewhere in the field of view of countless telescopes, going unrecognized because no one knew to look for it. It took specific gravitational analysis to predict its existence. It took dedicated surveys to begin searching for it, and it may still take years or even decades before we directly see it. The point is, it could have been found earlier. The data was always there. The methods just weren't. This is true of so many discoveries. We don't fail to find things because they don't exist. We fail to find them because we don't know how to look. And as our tools improve, as our understanding deepens, as our methods grow more sophisticated, we uncover what was always present. Each generation of astronomers finds things their predecessors couldn't. Each generation looks back at the previous era and wonders how something so obvious could have been missed. And the same will be true of us. Future astronomers, looking back at our era, will probably wonder how we could have missed Planet 9 for so long. They will probably take its existence for granted. They will probably look at our era of uncertainty as a kind of dark age, when the basics of the solar system were still being worked out. But here is something more profound. There is a sense in which Planet 9, whether or not it exists in the way we currently imagine, has already changed astronomy, because the search for it has driven new surveys, new instruments, new methods, new ways of thinking about the outer solar system. Even if Planet 9 turns out to be a statistical illusion, the effort to find it has produced enormous scientific value. We've catalogued thousands of new trans-Neptunian objects. We've improved our understanding of gravitational dynamics in the outer solar system. We've built new telescopes and developed new survey techniques. We've trained a generation of astronomers in the art of searching for faint, distant, slow-moving objects. The pursuit of Planet 9 has already paid dividends, regardless of whether the planet itself ever materializes. And there is something to be said for the value of pursuing something difficult, something uncertain, something that might not even be there. Science doesn't always reward certainty. Sometimes it rewards the willingness to ask questions whose answers we don't yet know. Sometimes it rewards the courage to chase phantoms that turn out to be real. Sometimes it rewards the persistence to keep looking even when years of searching have produced nothing. The astronomers who hunt for Planet 9, knowing they might be wrong, knowing they might never find anything, are doing something genuinely brave. They are committing their time, their reputations, their effort to a question that may have no satisfying answer. This kind of intellectual courage is what science is built on. It is what produced Leverrier's discovery of Neptune, even when the prediction seemed audacious. It is what produced Einstein's theory of relativity, even when the existing physics seemed adequate. It is what produced the discovery of dark energy, even when the assumed expansion rate of the universe was supposed to be slowing down. Every major advance in our understanding has come from someone willing to question what was assumed, willing to look in places where nothing was expected to be found, willing to entertain ideas that seemed wild at the time. The Planet 9 hunt is exactly this kind of endeavor. It is the modern equivalent of Leverrier's bold prediction, scaled up to the era of giant telescopes and global astronomical collaborations. And consider this. Even if Planet 9 doesn't exist as we currently imagine it, the question itself has revealed how much we still don't know about our solar system. The mere fact that we're seriously debating whether there's another massive planet beyond Neptune means our maps are incomplete. It means our gravitational accounting of the outer solar system has gaps. It means there are phenomena out there, whether one planet or many small objects or some exotic configuration, that we haven't yet characterized. This is a profound admission. It means our basic understanding of our cosmic home is still being written. We are not finished students of our own neighborhood. There's something poetic about this. We have sent spacecraft to every planet in the solar system. We have landed rovers on Mars. We have flown probes past Pluto and into the heliopause. We have mapped the surfaces of moons and analyzed the chemistry of comets. We have done extraordinary work understanding our local cosmic neighborhood. And yet, in the outer reaches of that same neighborhood, hidden in plain sight, may be a planet larger than Earth that we have not yet directly observed. The juxtaposition is striking. We are simultaneously remarkably advanced and remarkably ignorant. We know so much and so little at the same time. What does this tell us about the rest of the universe? If our own solar system can hide a massive planet from us for so long, what can we possibly say with confidence about systems light years away? When we observe exoplanets around distant stars, we're only seeing the ones bright enough, close enough, and well positioned enough to detect with our current methods. Most planets around most stars are probably invisible to us, hidden in ways even more profound than Planet 9. The galaxies themselves probably contain far more material, far more structure, far more complexity than we currently recognize. The universe is, in a sense, mostly hidden from us. We see only what our instruments allow us to see, and our instruments are far more limited than we sometimes acknowledge. This is a humbling thought, not a discouraging one, but a humbling one. It reminds us that science is an ongoing process, that our knowledge is always incomplete, that there is always more to discover. It reminds us that the boundary between the known and the unknown is closer than we sometimes pretend. And it reminds us that we should approach the cosmos with a kind of appropriate humility. We don't know everything. We don't even know most things. We are pieces of a much larger puzzle, and we are still figuring out where the edges of the puzzle even are. Planet 9, in this sense, is more than a planet. It is a symbol of how much we still have to learn, a symbol of how much remains hidden, even close to home, a symbol of the persistent mysteries that surround us, mysteries we can sense but not yet describe, mysteries that drive us to keep looking, keep searching, keep building better telescopes and developing better theories. The search itself is the point. The discovery, if it comes, is just one milestone in a much longer journey. And here is something to think about. Whether or not Planet 9 is real, the universe is full of similar mysteries. There are gravitational anomalies in other systems that astronomers are quietly investigating. There are unexplained signals in the cosmic microwave background that might be hints of new physics. There are large-scale patterns in galaxy distributions that don't quite fit our standard models. There are particles whose properties we don't fully understand. There are fundamental questions about the nature of time, space, and consciousness that physics has not yet answered. The Planet 9 hunt is just one of many fronts where humanity is pushing against the limits of what we know, trying to understand a universe that is far stranger and more complex than our intuitions suggest. Let me take you forward in time now, to the moment when this mystery finally resolves. To the day, perhaps just a few years from now, when an astronomer somewhere in the world opens up a new image from the Vera Rubin Observatory and sees something they weren't expecting. A faint point of light, slowly moving against the background stars, right where the predictions said it should be. The discovery moment. Imagine the scene. It is a quiet night in Chile, high in the Andes Mountains. The Rubin Observatory has been running its survey for months, taking images of the same regions of sky repeatedly, building up an enormous catalogue of moving objects. Software algorithms scan the data automatically, flagging anything that shifts position from one observation to the next. Most flagged objects are known asteroids or comets, identified within seconds and dismissed. But one flagged object isn't on any database. It is faint, magnitude 23 or so, near the limit of what the telescope can detect. And it is moving incredibly slowly, just a tiny fraction of an arcsecond per day. The kind of motion that would only be detectable by comparing observations months apart. The astronomer on duty pulls up the image. They check the database. They check the orbital catalogues. They check the list of known trans-Neptunian objects. Nothing matches. The object is unknown. They look at its predicted trajectory based on the few observations available so far. The orbit, when fitted preliminarily, is dramatically elliptical. The semi-major axis is enormous. The object is somewhere around 500 astronomical units from the Sun. The astronomer's hand pauses over the keyboard. They know exactly what they are looking at. They have known for years that this moment might come. The math has predicted it. The team has prepared for it. And here it is. A faint point of light, moving so slowly it almost doesn't seem to move at all, sitting in the predicted region for Planet 9. They don't announce it yet. They can't. Not based on a single set of observations. The data has to be verified. Follow-up observations have to be scheduled with other telescopes. The orbit has to be refined with multiple data points across multiple months. The brightness measurements have to be checked against thermal infrared observations to confirm the object's composition. There is a long process between the initial detection and the formal announcement. Months at minimum, possibly a year or more. But the discovery is real. They know it. Their colleagues know it. Within hours, news of the detection spreads through the global astronomy community, kept confidential at first, but eventually leaking out through the inevitable channels by which scientific gossip travels. Telescopes around the world are quietly redirected. Time on Hubble is requested. Time on James Webb is requested. Multiple observatories begin coordinated follow-up. Within weeks, the data starts pouring in. The object's spectrum is measured. Its thermal emission is detected. Its size is constrained. Its orbit is refined. And one day, perhaps a year after that first detection, the formal announcement is made. A press conference is held. A paper is published in Nature. A new world is officially added to the maps of the solar system. After centuries of searching, after decades of debate, after years of dedicated observations, Planet 9 has been confirmed. The reaction would be extraordinary. News headlines around the world. Special television programs explaining the significance, public lectures and interviews. The astronomers who made the discovery would become household names. Mike Brown, Konstantin Batygin, Scott Shepard, all the researchers who had been hunting for this world for so long would be vindicated. Their persistence would be rewarded. Their hypothesis, treated with skepticism by some for years, would suddenly be the foundation of a new chapter in planetary science. And yet, even in this moment of triumph, the story would not be over, because the discovery of Planet 9 would only be the beginning of investigating what it actually is. The early observations would tell us its approximate mass, its rough orbit, its general size, perhaps some basic information about its composition. But the deeper details, the atmospheric chemistry, the internal structure, the surface features, the question of whether it has moons, all of these would require extended observations over years or decades. We would have a new world to study, and studying it properly would take time. And there would be surprises. There are always surprises with new discoveries. The composition might be unexpected. The atmosphere might contain compounds we didn't predict. There might be moons that no one anticipated. There might be features that challenge our understanding of how such a planet could form or evolve. Every new world we've explored has surprised us. Mercury has water ice in its polar craters despite being closest to the Sun. Venus has incredibly powerful winds in its upper atmosphere despite its slow rotation. Mars has evidence of ancient liquid water and recent water flows. Jupiter has more moons than we knew about. Saturn's rings are far younger than we expected. Each world has revealed mysteries we didn't anticipate. Planet 9 would be no different. One question that would likely consume researchers in the years after the discovery would be the question of origin. Where did Planet 9 come from? Was it formed in our solar system and scattered outward by the gas giants? Was it captured from another star system during our Sun's formation in a stellar cluster? Was it formed in place through some process we don't yet understand? Each origin scenario would predict different chemical signatures, different orbital parameters, different physical properties. By studying the planet carefully, we could potentially distinguish between these possibilities. We could read its history written in its composition and structure. We could learn not just what it is, but where it came from and how it got there. This would have implications far beyond Planet 9 itself. If we determined that Planet 9 is a captured exoplanet, it would tell us something important about how often star systems exchange material during their formation. It would suggest that other solar systems probably have similar refugees, captured worlds living in distant orbits. It would change our understanding of how planetary systems evolve. If we determined that Planet 9 formed in our own system and was scattered outward, it would tell us that violent planetary migration was an important part of our solar system's history. It would confirm that the chaos of the early solar system was significant enough to fling massive worlds onto extreme orbits. It would suggest that other star systems probably had similar chaotic phases, ejecting some planets while keeping others. Either way, the discovery of Planet 9 would not just be the addition of one world to our cosmic catalogue. It would be the addition of a story, a history, a new piece of evidence about how our solar system, and by extension other solar systems, came to be. The planet itself would be only the visible part of a much larger narrative. The narrative is what scientists really want to uncover. But let's also consider another possibility. What if Rubin completes its full 10-year survey without finding Planet 9? What if the planet, despite years of searching, simply isn't detected? What would that mean? It would mean we have to reconsider. The gravitational anomalies that suggested Planet Nine's existence would still be there. The clustering of distant orbits would still need an explanation. But if no planet is found within the predicted parameters, we'd have to look for other explanations. Maybe Planet 9 is smaller and fainter than we thought, beyond Rubin's detection capability. Maybe it's in a wider orbit than predicted, putting it in regions Rubin didn't sufficiently survey. Maybe it's a primordial black hole and there's no light to detect at all. Maybe the gravitational signature is caused by something else entirely, perhaps a diffuse population of small bodies, perhaps an unknown effect of the sun's motion through the galaxy, perhaps a statistical artifact of how trans-Neptunian objects are detected. In this scenario, the absence of a discovery would itself be a discovery. It would tell us that our current theories about Planet 9 are wrong. It would force a major reconsideration of what the gravitational data actually means. It would open new lines of investigation. The hunt wouldn't end. It would simply shift to other possibilities. The mystery of the outer solar system would remain unsolved, but our understanding would have advanced. We would know what isn't out there, even if we still don't know what is. This kind of null result is common in science, and it's almost always informative. The discovery that something doesn't exist where you thought it would is just as scientifically valuable as confirming that it does. It rules out hypotheses. It narrows the space of possibilities. It pushes researchers to develop new ideas. Every careful negative result is a step forward in understanding, even though it doesn't generate the kind of headlines that positive discoveries do. There's a third possibility too, one that is perhaps the strangest of all. What if Rubin finds something, but it isn't Planet 9? What if the survey detects a new object in the outer solar system, something we didn't predict, something that doesn't match any of the existing hypotheses? Astronomy is full of accidental discoveries. The cosmic microwave background was found by researchers looking for something else entirely. Pulsars were discovered by a graduate student investigating radio noise. Quasars were initially mistaken for radio stars. The history of science is full of moments when researchers were looking for one thing and found another. Rubin's survey, designed to detect Planet 9 among many other targets, will inevitably uncover surprises that no one expected. Perhaps Rubin will find a new dwarf planet larger than Eris or Pluto. Perhaps it will find a moon orbiting a distant Kuiper belt object that nobody predicted. Perhaps it will find an interstellar object passing through our solar system, larger and more dramatic than the previous interstellar visitors. Perhaps it will find something genuinely strange, something that defies easy categorization, something that opens up entirely new questions about what exists in the outer solar system. Whatever Rubin finds, it will probably exceed what we currently imagine. That's the nature of major surveys. They don't just answer the questions we asked. They reveal questions we hadn't thought to ask. This is what makes the next few years so exciting. We are entering an era when the outer solar system is being mapped with unprecedented precision. The technology has finally caught up with the questions. The instruments are in place. The surveys are beginning. The data is starting to flow. Whether or not we find Planet 9, we are about to learn enormous amounts about what is out there in the dark beyond Neptune. And that's worth celebrating. Even if Planet 9 turns out to be a phantom, the search for it has driven advances in astronomy that will pay dividends for decades. Even if Rubin finds nothing at the predicted location, it will find many other things. Even if our current theories about the gravitational anomalies turn out to be wrong, the process of trying to understand them will deepen our knowledge of the solar system in ways we can't yet fully appreciate. We have reached the end of this journey through the outer darkness, and yet in many ways we are at the beginning, because Planet 9, whether it exists or not, represents something larger than itself. It represents the persistent mystery of our cosmic neighborhood. It represents the boundary between what we know and what we don't. It represents the ongoing process of discovery that has defined human civilization since we first looked up at the night sky and asked what was there. Let me try to summarize what we have explored. We began with the gravitational anomalies that suggested something was out there. the strange clustering of distant trans-Neptunian objects, all aligned in ways that random chance can't explain. We followed the work of astronomers like Mike Brown and Konstantin Batygin, who took those anomalies and turned them into a hypothesis. We discussed the predicted properties of this hidden world. A super-Earth or sub-Neptune, 5 to 10 times the mass of our own planet, sitting somewhere between 400 and 800 astronomical units from the Sun, completing a single orbit every 10,000 to 20,000 years. We explored why it has been so difficult to find, the brightness problem, the vast search area, the challenge of detecting slow-moving objects against crowded background stars. We discussed alternative explanations. The primordial black hole hypothesis, the diffuse ring of mass hypothesis, the possibility that the entire anomaly is a statistical illusion. We examined what Planet 9 would actually be like if it exists. The brutal cold, the perpetual twilight, the silence and the stillness of a world that has never known life. We considered its possible origins, whether it formed in our solar system, was captured from another, or emerged through some process we don't yet understand. We placed Planet 9 in the broader context of planetary science, the discovery of exoplanets and how it has reshaped our understanding of what is possible in solar systems. The realization that super-Earths and sub-Neptunes are common around other stars, even though we don't appear to have any. The way Planet 9, if real, would make our solar system look more typical of the galaxy. We discussed the history of similar searches, the story of Vulcan, the planet that didn't exist, the story of Planet X, the prediction that led to the accidental discovery of Pluto, the cautionary tales that shape how modern astronomers approach the announcement of new worlds. We confronted the philosophical implications. What does it mean that something so massive could be hiding so close to home? What does it tell us about the limits of our knowledge? How does it fit into the long story of cosmic demotion, in which every major discovery has further humbled humanity by revealing how much we don't know? We thought about the future, the Vera Rubin Observatory, and what it will likely reveal, the discovery moment that might be just a few years away, the possibility of confirmation, the possibility of a null result, and the possibility of accidental discoveries that exceed anything we currently imagine. Through all of this, one theme has emerged. The universe is stranger and more complex than we yet understand. Our maps are incomplete, our models are limited. Our knowledge, despite all our scientific achievements, is still being written. Planet 9 is a symbol of this incompleteness. It represents the gap between what we think we know and what is actually out there. It reminds us that even our own cosmic backyard contains mysteries we haven't yet solved. And here is something to think about as we close. The astronomers who hunt for Planet 9 are doing more than just searching for one planet. They are part of a much larger tradition, a tradition that stretches back to the first humans who looked up at the night sky and wondered what was there. A tradition that includes every astronomer who patiently observed the stars before us, every philosopher who tried to understand the cosmos, every mathematician who developed the tools we use to analyze it, every engineer who built the instruments we use to see it, every researcher who carefully tested hypotheses and revised them when the evidence required. This tradition is one of humanity's most remarkable achievements. It is the slow, careful, persistent process by which we have come to understand our place in the universe. It has produced the knowledge that fills our textbooks and powers our technology. It has revealed that we are tiny beings on a small planet orbiting an ordinary star in an unremarkable corner of a vast galaxy. It has also revealed that, despite our smallness, we possess something extraordinary: the ability to comprehend, the capacity to ask questions and seek answers, the desire to understand things that have no immediate practical benefit simply because the questions themselves are worth asking. Planet 9 is one of those questions. Whether or not it exists, the search for it embodies what science is supposed to be: the willingness to follow evidence wherever it leads, the patience to keep looking even when years of searching produce nothing, the intellectual honesty to consider alternatives when the obvious explanation fails, the collaborative effort of researchers around the world, building on each other's work, refining ideas, testing predictions. All of this happens in the service of answering a question that, on its surface, doesn't directly affect anyone's daily life. We are not going to harvest resources from Planet 9. We are not going to live there. The planet, if it exists, has no immediate practical relevance to us, and yet we search for it. We build telescopes worth billions of dollars to look for it. We spend careers studying it. Why? Because understanding matters. Because knowledge has value beyond its applications. Because the act of discovery is one of the most meaningful things humans can do. We are, perhaps uniquely in the universe as far as we know, beings capable of wondering. And wondering leads to looking, and looking leads to finding, and finding changes us. It expands our sense of what is possible. It deepens our appreciation of what exists. It connects us, in some intangible way, to the broader fabric of reality. Think about what it would mean to live in a moment when humanity finally confirms the existence of a ninth major planet, the first new planet discovered in our solar system in nearly 2 centuries. Or alternatively, think about what it would mean to live in a moment when, after years of searching, we definitively conclude that no such planet exists, and we have to find new explanations for the gravitational anomalies we've observed. Either outcome would be historic. Either outcome would mark a major moment in the long story of cosmic exploration. And we are living in the brief window when this resolution is approaching. We will likely know the answer within the next decade, possibly within just a few years. Future generations will read about this period as one of the great moments in the history of astronomy. We are alive to witness it. That's something worth appreciating. The vast majority of humans who have ever lived had no chance to follow the unfolding of major scientific discoveries in real time. They lived in eras when knowledge advanced slowly, when major breakthroughs came once a generation, if at all. We live in an era of accelerating discovery. We can follow the news from observatories around the world. We can read the papers, watch the press conferences, listen to the interviews. We can feel the tension of unresolved questions and the excitement of approaching answers. This is a privilege of our particular moment in history. We should not take it for granted. And whatever the resolution of the Planet 9 mystery turns out to be, it will not be the end of the story. There will be more questions, more mysteries, more researches. The outer solar system will continue to reveal its secrets slowly over decades as our tools improve. New planets, new dwarf planets, new objects we haven't categorized yet will be found. Some will be in the predicted region for Planet 9. Some will be in places we hadn't thought to look. Some will challenge our existing models in ways we can't currently anticipate. The frontier of knowledge will keep expanding. The boundary between the known and the unknown will keep shifting outward. For those of us who find these questions fascinating, this is wonderful news. It means there is always more to learn. There is always more to explore. There is always another mystery waiting to be uncovered. The universe is inexhaustible. Our curiosity, properly applied, has no shortage of material to work with. And the joy of discovery, the moment when something previously hidden is finally revealed, is one of the deepest pleasures available to a thinking mind. So as we close, let me leave you with this. Somewhere out in the cold dark beyond Neptune, there may be a planet, a massive, frozen, distant world that has been orbiting our sun since before life existed on Earth. It may have witnessed the formation of the inner planets, the development of the moon, the evolution of life, the rise of civilization. All of human history may have unfolded within a single year of its slow orbit. If it exists, it is waiting for us to find it. Not literally, of course. It doesn't know we exist. It doesn't care about our search, but there is something poetic about imagining it out there, drifting through the darkness, while astronomers on a small planet many billions of kilometers away point their telescopes and search. And someday, possibly soon, we will see it, or we will conclude that it isn't there. Either way, we will learn something. Either way, the search will have been worthwhile. Either way, the universe will have taught us another lesson about the limits of our knowledge and the depth of what remains to be discovered. Thank you for joining me on this journey through the outer solar system and the search for Planet 9. If you found this exploration valuable, a like or subscribe would mean a lot. It helps this channel continue making these deep explorations of space and our place within it. Share this video with anyone who loves a good cosmic mystery. Comment below with your country of origin and your thoughts about what Planet 9 might really be. A planet, a black hole, something else entirely. Whatever you believe, the universe will eventually reveal the answer. We live in extraordinary times, times when we can see deeper into space than ever before, times when we can study cosmic dawn and search for hidden worlds in our own backyard, times when the answers to questions our ancestors couldn't even ask are finally within reach. Make the most of this moment. Keep wondering, keep questioning, keep looking up at the night sky and asking what is out there. Because the universe is vast, ancient, and full of surprises. And we, tiny beings on a small planet, have been given the remarkable gift of being able to understand it. Good night.